For optimization problems, here are a few things that you should keep in mind when you're solving these. You have to assign variables to given quantities and the quantities to be determined. When necessary, it might be helpful to draw a sketch. The second step, you want to write an equation to be optimized in terms of the two variables. You want to find the values that are sensible or feasible for the problem situation where the derivative of the equation to be optimized is equal to 0. And then you want to verify you have a minimum or a maximum using the first or second derivative test. Don't forget to test the endpoints as well, as that might actually, there might be a maximum min that occurs there. Okay? And so here are just a few things to keep in mind. And so when we're going through these problems, you'll see how we actually do all 4 of these steps. All right? So for the first example, I'm going to switch up to the board. Okay, so the first one says the product of two positive numbers is 48. Find the numbers so that the sum of the first number plus 3 times the second number is a minimum. So the first thing we need to do is we need to assign variables to the given quantities and the quantities to be determined. So x is going to represent our first number, and y is going to represent our second number. All right? And then step 2 says to write an equation to be optimized. In other words, minimized or maximized in terms of the two variables. Well, in the problem, it says that the product of two numbers is 48. So that's x times y is 48. Okay? The product of two positive numbers is 48, product multiplication. It's find the numbers so that the sum of the first number plus 3 times the second number is a minimum. So the sum of the first number, so the first number is x, plus 3 times the second number is a minimum. This is going to be the equation to be optimized because I'm looking for the values so that that becomes a minimum. Okay? And it's given to us right there in the problem. Now, you're probably wondering, well, why did I put down the x times y equals 48? Because when you're doing optimization problems, you're going to need 2 equations, okay? Because if you notice, in the one that I have to minimize, I have 2 different variables here. I'm not concerned about s, I'm concerned about the fact I have an x and a y. And honestly, when we're trying to find the derivative, we need to have the same variable. So that's where this first equation, this x times y equals 48 comes into play, because what I'm going to do is I'm going to solve for one of my variables, and then I'm going to plug it in, okay? So I'm going to take this equation, and I'm going to go ahead and solve for y so I can get everything in terms of x. So to solve for y, I'm just going to divide both sides by x, and this is what y equals. So that way, I can go and plug it in, and now I have, let's see, 48 times 3 is 144? No, what is it? Yes, 144. So now I have an equation that has this one variable that I can easily take the derivative of, okay? So that was step 2. Step 3, it says find the values that are sensible and feasible for the problem where the derivative of the equation to be optimized equals 0. Where the derivative equals 0, which means that I have to take the derivative of this s function, okay? So the derivative of s is going to equal 1. Since my x is at the bottom, I'm going to rewrite it as 144x to the negative 1. It makes it a lot easier to find the derivative of that. It's going to be a negative 144x to the negative 2. And then I don't want any negative exponents, so I'm going to bring it back down to the bottom. So now I'm going to set that equal to 0, and I'm going to solve. So I'm going to subtract 1. Two negatives can turn into a positive. Then I'm going to multiply both sides by x squared to get x from off the bottom. So I have 144 equals x squared. And then I take the square root. And x equals plus or minus 12. All I'm doing is solving for x. That's a regular equation that we can solve for. Now, I only want positive numbers here. So the only x value I'm concerned about is the positive 12. That's the x number that I'm concerned about. So I need to make sure that this is indeed a minimum. So in order to determine if x, a critical point, a critical number, is a minimum, I have to plug it into my second derivative. So the second derivative of s is going to be 288 over x cubed. Now, if you're wondering where's the work for that, well, I'm running out of space, as you can see, so I want you to find the second derivative on your own. But I promise you it should be 288 over x cubed. All right? So then I'm going to plug in 12. And if it's a minimum, then this should come out to be a positive number. So when I type that in, I'm going to get 288 divided by 1728. And in actuality, I'm not really concerned about what the number is. I'm more concerned about the fact that it is a positive number. And if it's positive, that means that there is indeed a minimum based off of our second derivative test. So that means that 12 is my first number. To find my second number, to find my y, all I do is I plug it back in and find out that y is 4. And there are my two numbers that are going to, that basically cause this to be a minimum. All right? Let's try the second problem. It says a rectangular plot of farmland is enclosed by 180 meters of fencing on 3 sides. The fourth side is bordered by a stone wall. Find the dimensions of the plot that are enclosed, that enclose the maximum area, and then find the maximum area. So the first step is we want to assign our values and maybe even draw a quick sketch. I think a quick sketch might be helpful here, okay? So here's our stone wall. A rectangular plot of farmland is enclosed by 180 meters of fencing. We have one side is x, one side is y, or you could do length and width. It really doesn't matter. Okay? And so now, so basically x represents a width, y represents our length. And we have to find our equation to be optimized. Well, I'm trying to find the maximum area. So area is the equation that I need to maximize. Area of a rectangle, x times y, length times width, base times height, basically one side times the other side. All right? But now I'm at that point where I have two variables. I have to have one variable, so I need my second equation. I know that there's 180 meters of fencing. Fencing. It goes around the rectangular plot of farmland. Around, that's perimeter. So my perimeter is x plus y plus x. So the amount of fencing I have available is 180. That equals 2x plus y because I combine like terms. So if I solve for one of my variables, and then I'll be able to basically plug it in. Okay? So I'm going to solve for y just so I don't have to deal with any fractions. So 180 minus 2x equals y. So now I'm going to go back and plug it in. And I see that the equation I want to optimize, or I want to find the maximum of, is this equation right here. Okay? So now it's time to find the derivative. That's our next step. So it's 180 minus 4x, and I need to set that equal to 0. Subtract 180 from both sides, divide both sides by -4, and I'll see that x is going to be equal to 45. Okay? So one of my dimensions is going to be 45. Now, I have to test that. I have to test to see if that is indeed going to be a maximum. If it's a maximum, that means when I plug it into my second derivative, I should get a negative number. My second derivative is a -4. Ooh. Now, because it doesn't matter, you know, if I plug in 45 in, no matter what, I'm still going to get a negative number, right? And a negative number represents a maximum. So this is indeed true. This is indeed that maximum. All right? So my dimensions are 45 my units, 45 meters. And then to find my y, all I gotta do is plug it back in down here, which is 90. So my dimensions of the plot that enclose the maximum area are 45 meters by 90 meters. And then my maximum area will be 45 times 90, which is 4,050 meters squared. Okay? Pause this video and try this example. Okay? Really try this example. So I don't know if you noticed, but the problem base will tell you what two equations you'll need. In this particular one, you'll need surface area and, well, actually this one is a mistype. It should have actually said a volume. Okay? So yes, surface area and volume. Those are the two equations that you'll need here. Okay? So it says the dimensions of an open box with a square base and a surface area of 192. We're trying to find the maximum volume. Okay? Well, a box with an open base, okay, or open face, so this one is the open one, has a surface area of 192. Okay? Let's label step one. Let's label, okay? Since it's a square base, I know my length and my width are the same. Okay? But my height is different. So I have my x and h. Those are my variables. One represents length, one represents width, the other one represents height. Now surface area normally is basically the sum of all of the faces. Okay? Well, I have my square base at the bottom. The area of that is x squared. And then one side of this box would be x times h. But I have 4 sides here. So it's going to be 4xh, because that represents basically the area of all 4 sides. So then when I add the area of all 4 sides to my base, I have my surface area, which should equal 192. And I'm trying to maximize my volume. Well, volume, if you recall, for a box is length times width times height. So basically x squared times h. All right? Now, so there's my equation that I need to optimize. But the thing is, I have to solve for one of the variables in my surface area formula, so that way I have just one variable. And in this case, I'm going to solve for h. So I'm going to subtract x squared over and divide everything by 4x. So that way, I will solve for h. So I'm going to have a negative x over 4 plus, let's see, 192 divided by 4 is 48 over x. Okay? Now, to go from here, I need to take into account that I have to plug in, okay? Plug in h. So my original volume formula was x squared times h. So when I plug in h, I'm going to have negative x over 4 plus 48 over x. And when I distribute, I'll get negative x cubed over 4 plus 48x. And this is the equation that I need to optimize. So I'm going to take the derivative. So this will be negative 3/4 x squared plus 48. I have to set that equal to 0, and now I have to solve. Okay? So I'm going to change the slides here, and I'm going to solve this. Negative 3/4 x squared plus 48 equals 0. So I'm going to subtract 48 to the other side. Okay, I'm going to multiply by a negative 4/3 to basically get rid of my fraction altogether. When I do that, I'm going to get 64. The square root of that is a plus or minus 8. Now, x is supposed to represent a dimension of a box, so I'm only concerned about my positive value. So 8 represents my length and my width, okay? Represents my length and the width of my box. All right? Now to find my height, remember, height was this formula right here. So all I have to do is plug in. So that's negative x over 4 plus 48 over negative x, or over x, which was a positive 8, sorry. All right, sorry I have to keep flipping back and forth, but I don't remember what the equation were. So now this will be a negative 2 plus 6, so my height is 4 centimeters. Okay? Try this one. Pause the video. Try this one. All right, so here's the last one. The cost C of ordering and storing X units of product is represented by that equation. A delivery truck can deliver at most 200 units per order. Find the order size that will minimize the cost. So we already have an equation, so that's good. We do need to take into account the fact that the delivery truck can deliver at most 200 units. So that means they can either order carry 1 unit or up to 200 units. So we have a restriction here. We have endpoints that we need to test. So we find our first derivative, and then we set it equal to 0. When I set it equal to 0, I find that x should be a positive 100 once I solve. So now, in order to figure out which order size will minimize my cost, that means I need to use the second derivative test, not the second derivative test. I need to plug in those values, the 1, the 100, the 200, and I need to see which one is going to give me my minimum value, okay? So when I plug in 1, I get 10,001 products. That's a lot. That's not my minimum. When I plug in 100, I get 200 units, and then when I plug in 200, I get 250. So my minimum is right here, which means that my minimum cost will come when I get delivered 100 units. And so that is my final answer. All right, if you have any questions, let me know.